In this short review video, we're going to be talking about the properties of DNA and particularly base pairing. So there's a few things that I want you to recognize in this image here. The first is the anti-parallel strands that we see between the two DNA strands here. And what's meant by anti-parallel is that one strand is going from 5' to 3', and in the same direction, the other strand is 3' to 5'. In other words, they're in the opposite orientation of directions. Right? The other thing that you should notice here is that we basically have what I kind of use as an analogy of a ladder. So we have the handrails of the ladder, meaning the backbone of the DNA, kind of going along the sides here, and then we have the rungs or the steps of the ladder that go in between. And making up the backbone of the DNA, or the handrails of the ladder here, is the phosphodiester linkages. So we have these phosphate groups, all right? So if we looked closely at the phosphate group, we would see a phosphate with a lot of oxygens, to be precise, around it. And then one of those would be connected to the sugar right here. And then that, with its base, is a single nucleotide. So we have a phosphate, sugar backbone, and then the base coming out of the side. So I'm going to use my bases over here to the right to show how this backbone linkage, this phosphodiester linkage, works to link together the single strands of DNA. So here we have the adenine, and the base is connected to a sugar at this C1 residue. So the C1 residue is part of a sugar that has 5 carbons. So carbon 2 would be down here, carbon 3, carbon 4, and then carbon 5 is up off by itself. And linked to that carbon 5 of this sugar is a phosphate group. And linked to this carbon 3, since this is deoxynucleotides, carbon 2 doesn't have an oxygen, but carbon 3 does have a group. And so this would be why this is in the 5' to 3' directionality, because we have the 5' carbon here and the 3' carbon down here. Now this links to the next one. So on this guanine here, we also have the same sugar. And then off that sugar comes our phosphate group. And that phosphate group hooks to this oxygen here of that carbon, the hydrogen's released, and this is the phosphodiester linkage. So the sugar of one base is linked to the phosphate of the next one. And down here, if we kept going, this would be linked to the next phosphate group as well. The anti-parallel strand just basically is in the opposite direction. So you basically have your sugar looking like this. Sorry, that's the phosphate group in the middle there. So here we have the 3' to 5' directionality, and this phosphate group, basically this base would have its own sugar here. And this carbon here would be linked to that phosphate group right there, and so we have the 3' to 5' groups. Now I do need to make a little correction here. The C5 would be linked to an oxygen that is linked to that phosphate group. So the phosphate group is always linked to the carbon through that oxygen right there. Sorry about that. So this gives us the covalent linkage of the rungs of the ladder. So each of these rungs here are very tightly bound together. So this rung with those bases can be separated from that rung. But normally this is held together by base pairing, and this is the last thing I want to talk about. So base pairing holds the two strands together by hydrogen bonding of our bases in the middle here. So here we have an adenine bound to a thymine, and we know that adenines are our purines, and in other words, they have 2 rings, and guanine is also a purine. And then thymine and cytosines are pyrimidines with a single ring, just one ring in the base. Now they line up together because of hydrogen bonding of base pairing. When adenine is lined up with thymine, we get perfect orientation for hydrogen bonds to form. When guanine and cytosine are lined up together, we also get that perfect orientation for hydrogen bonding. So here we can see a nitrogen and hydrogen at the top here of adenine. So I'm looking at this group right here. We know that nitrogen-hydrogen is a polar bond, and so this is going to have a positive dipole. The nitrogen has a negative dipole. On the other side over here, we see the carbon-oxygen bond, and we know that oxygen has a negative dipole, carbon has a positive dipole. So this negative dipole aligned to the positive dipole there gives us room for a hydrogen bond. Same thing looking a little bit lower. We have this nitrogen here, which has a negative dipole, hydrogen a positive dipole because that's a polar bond. This nitrogen here has a negative dipole because it's bound to the carbons, and nitrogen has higher electronegativity, so its dipole is negative. And that negative dipole nitrogen aligned to the positive dipole hydrogen gives us room for a hydrogen bond. Now, adenine and thymine only have 2 hydrogen bonds, and the reason for that is even though this looks like it should have potential for a hydrogen bond, this oxygen does indeed have a negative dipole because it's bound to carbon, but this is a carbon-hydrogen bond, and we know carbon-hydrogen bond is a nonpolar bond. Therefore, this hydrogen does not have a dipole, and since the hydrogen does not have a dipole, it cannot form a hydrogen bond over here. So adenine and thymine only have 2 hydrogen bonds. If we look at guanine and cytosine, we can basically do the same thing. Carbon-oxygen, oxygen is going to end up with a negative dipole. Nitrogen-hydrogen, hydrogen has a positive dipole, we have a hydrogen bond. Nitrogen-hydrogen, hydrogen again has the positive dipole. Nitrogen-carbon gives nitrogen a negative dipole there, hydrogen bond. Nitrogen-hydrogen, hydrogen has a positive dipole. Carbon-oxygen, oxygen has the negative dipole, there's your hydrogen bond. If these bases were to line up in any other way, guanine tried to line up with thymine, adenine with cytosine, and so forth, those different dipoles would not align such that those hydrogen bonds can form. And that's why guanine always binds to cytosine with 3 H bonds, and adenine always binds to thymine with 2 H bonds. Remember that covalent bonds are when atoms are sharing electrons, and those are very strong. Hydrogen bonds are not a shared pair of electrons. They are just when opposite dipoles attract, because remember, opposite charges attract, and therefore a negative dipole is going to be attracted to a positive dipole. And that's what creates those hydrogen bonds that hold these base pairs together. If you're still having a hard time recognizing polar bonds and dipoles, you should go back and review one of our earlier videos on electronegativity, as that's going to be very important. All right, thank you very much.